We continue with section 3.2 from the book. As special cases of rings, we introduced integral domains and fields. These are classes of rings, and we remember the example that Z, the ring of integers, is an integral domain while not a field. Reverse counterexamples are not available, which is an interpretation of Theorem 3.8, which says that every field is an integral domain. So, field but not integral domain cannot happen, while integral domain, while not a field, indeed happens. Z gives us an example. One can reformulate that as 12 in our list of requirements in the definitions implies 11. Both are sort of analogs of multiplicative analogs. Of requirement 5 for the addition. So we have a requirement for the addition that certain equations always are solvable. We gave two analogs 11 to be an integral domain is weaker than 12 to be a field. Now I want to really prove that it is indeed weaker, meaning every field is an integral domain. Proof: we say that let R be a field pick and assume, not even pick, assume AB is 0 in R with both A and B elements of R, of course, are we want to prove that at least one of them must be 0. So we assume that B is not 0 and prove that then A must be 0. So what I want to prove, if wanted, if B is not 0 in the ring, in our field, then A is 0 in the ring. I thus assume that B is different from 0, and we'll go to prove that A is not different from 0. B is not 0 implies then, by the definition of field 12, the equation Bx is 1 in R has a solution. You remember the definition of field. It was a ring with identity, so we use the fact it's commutative ring with identity. We use the fact that we have an identity, and 12 in the definition of field requires that this equation has a solution. So let X be the solution, or a solution. Let X be a solution. I don't need uniqueness here. Let us, and we have not proved that yet, let us multiply this equation by X. We multiply both parts of AB equals 0 in R by X. What we produce is a B X. I will put parentheses. AB equals 0. AB times X equals 0 X. Now, we have requirement 7 in the definition of a ring, that's associativity of multiplication, which tells us that A, B multiplied by X is equal to A, B multiplied by X. So the parentheses which I put there for precision actually is only extra care. They do not matter. And Bx, X was the solution to this equation. So Bx is 1. A 1 R. The definition of identity element 10 in the definition of ring tells us that a identity 1 R, if it exists, is the neutral element for multiplication. Any element multiplied by this element stays untouched. So by 10, this is A. The left-hand side, from 7, the first equality, or let me write it this way, better possibly, So I will write 7, the associativity here. And after that, we got R. So this is the transformations of the left-hand side. So the left-hand side is A, first by 7, and after that by Bx is 1 here, and after that by 10, by assumption, this assumption, and by 10. As to the left-hand, so we get A equals, as to the left-hand side, we just proved this statement from theorem 3.1 by theorem 3.1, which we have proved in the previous fragment, where in the previous fragment we have that this is 0R. So, what we wanted this statement: if B is not 0, then N is, then A is. We assumed that B is not 0 and proved that A is equal to 0. That's exactly what we wanted here, and thus we proved the theorem. Every field is an integral domain. We prove that a field satisfying 12 has a requisite property to be an integral domain, satisfies 11. Otherwise, as this example of the ring of integers show, is not true. Not every integral domain is a field. In the connection with integral domains, there are a couple of entries of our dictionary. So that's terminology, zero divisor, that's definition. Zero divisor is an element in a ring or is an element of the ring which satisfies first, the element is not 0 in R, and second, there exists a non-zero element in the ring such that AC is 0 in R. Such an element so that it is not 0, but multiplied by another non-zero element produces a 0 is called the zero divisor. As an example, and Z mod 6, 2 and 3 are zero divisors. Neither of them is zero, but their product is 6, which is 0 in this ring. The class of 6 is same as the class of 0 in Z mod 6. By definition, an integral domain has no zero divisors. This is a restatement of the condition 11. This condition, that is what we dealt with. If product is 0, then one of the factors must be 0. So one can reformulate with the notion of zero divisors, one can reformulate of the definition of integral domain integral domain is a commutative ring with identity one different from 0 without zero divisors, which this ring has no zero divisors. The requirement 11 was nothing but a requirement in this terminology was nothing but a requirement that integral domain does not have zero divisors. In an integral domain, in the absence of zero divisors, cancellations turn out to be possible. That is what theorem 3.7 tells us. Let R be an integral domain so an ABC elements of R with A different from 0. We have that AC equals AB implies C equals B. This is an analog. This is an analog for the operation of multiplication of theorem 3.4, which claims a similar property for addition. For addition. For addition, this is true in any ring. For multiplication, we're going to require integral domain, otherwise, maybe not true. I will not explain the whole proof. It is in the book, but I will give some. I will put some remarks about the proof. Now, first of all, roughly the proof is obtain A times C minus B equals 0 in the ring, and use the fact that use A is not 0, and in the integral domain, product is, we have integral domain, product of two elements A and C minus B is 0, A is not 0, so C minus B must be 0, because by the definition of integral domain. So C minus B is 0 means exactly C equals B. What that is, very rough outline of the proof. But what I want to emphasize, it is not possible. Oh, let me. Important remark, it is not possible to multiply this by A inverse. To get C equals B. Because A inverse may not exist R is assumed to be merely an integral domain not necessarily a field. So you cannot just take this identity and multiply by A inverse to get C equals B, because there is nothing like A inverse. Look, Z is an integral domain. It's far away. Z is integral domain, which is not a field. For a number 3, there is no 3 inverse in Z. So you cannot, integral domain may not have A inverse. You cannot multiply. It is possible to multiply by an inverse in a field. In a field, in contrast, in a field, twelve claims the solution for AX equals 1R exists as soon as A is not 0 in R. So then, if the condition here was not integral domain but a field, you can multiply by inverse. In this connection, we have definition. Again, that's terminology. And now the entry to our algebraic dictionary. An element, its definition in the book, an element of a ring is called a unit. If in a ring with identity, sorry, otherwise makes no sense. In a ring R with identity 1R is called a unit if there exists an element U in the ring such that AU is 1 in the ring same UA. So that is invertible element in a ring is called a unit. So that the equation, this kind of equation, has a solution U multiplied by some U from right to left. This ring with identity is not necessarily commutative, so I have to write both conditions AU and UA. I require them both to be one identity in the ring. In this case, the element is called unit. So U is referred to as multiplicative inverse of A. Of course, if A is a unit, then U, its inverse, is also a unit, which comes from the same requisite. Example 4 in the book The only units in the ring Z, Z is a ring with identity moreover a commutative. One identity is number 1. The only units in this ring are 1 and -1. 1 times 1 is 1. 1 is number 1. By coincidence, is 1 identity in the ring Z. -1 times -1 is 1. So -1 multiplicative inverse of -1 is -1 itself. Both are units, and it is more or less obvious, or look at the book at the example 4. They explain a little bit more there. These are the only units in the ring of integers. The definition of field can be, from the definition of field, we see that the field is commutative, so we don't need two of them, and the 12th definition of field requires the equation to have a solution as soon as A is not 0. So from in a field any non-zero element is a unit. And other way around, one can reformulate the definition of a field using this terminology, so reformulation of the definition field as a commutative ring with identity which is different from 0 in the field, such that every non-zero element is a unit. So every non-zero element is a unit. This is a field. Notation for an inverse. We have U here. So notation A inverse for U such that AU is 1 is R is UA. So can we denote this U as A inverse, which is pretty naturally will have A inverse is 1 as usual. It's possible. This notation is possible. However, only after we do some work the following proposition. Proposition or f a multiplicative inverse for some element in the ring exists, the ring with identity exists, then it is unique. Then we can call it A inverse as soon as we prove the uniqueness. Otherwise, if it is not unique, notation A inverse become misleading. But in this case, well, like we can easily prove the uniqueness and justify in this way the notation A inverse for the inverse of an element of a unit. Here is the proof of this proposition. We assume we have two of them. A u1 is 1r, and this identity, and this is u1a, and at the same time a u2 is identity, and this is u2a. We want to prove that u1 is equal to u2, whatever u1 and u2 are, that there is no more than one element. If somebody comes with another one, it is the same still. So from this, we assume that, and from these assumptions, we derive that u1, this is equal to u1, 1, simply because by the requisite property of identity, we can multiply by identity always without changing the element. This is equal to, or this identity is equal to a u2, u1, a u2, because a u2 is identity. So we wrote this identity as a u2. Now, in fact, there should be parentheses here, but we use associativity, which simply write it as a product of 3, and again use associativity to associate first u1 and a. u1a is identity from here. u2 and identity times u2 is u2 by the property, the requisite property of identity. So we proved that whatever elements u1 and u2 satisfy the property to be inverse to A, these two elements must coincide. u1 must be equal to u2. Thus, that justifies the notation A inverse for the inverse of a unit. So, in the next fragment, we will continue dealing with section 3.2, namely with integral domains and fields. We'll address an interesting argument which claims that under some condition in an integral domain must be a field. Thank you for listening.